My name is Vincent Guiteau. I'm working for Linaro in the kernel working group. And today I'm going to speak about energy-aware scheduling and the rework that we are trying to get merged in mainline. So we have discussed about these changes in the number of various different conferences. And today I will provide you just a short summary. I mean, it's a summary of 2 of the 50-minute talk that I have to summarize in 20 minutes. But yeah, anyway, if you have any question, don't hesitate to interrupt me, and we can follow up after the talk if needed. So the current energy-aware scheduler, which is there now for years. So yeah, we have a number of problems which are there for a while and which are more and more visible when we are trying to do energy-efficient task placement. And they are even more visible now that we have uclump, for example, or that we have more and more thermal mitigation and pressure on the system, which means that the OPP, the frequency selection, does not always follow exactly the utilization of the CPU because of latency, because of other things. So that creates some behavior which are not always handled correctly by the current energy-aware algorithm. So that's one first thing. The other thing is that right now the ES is only happening when a task wakes up. When a task wakes up, we take a snapshot and we decide which CPU is the best one. We put the task, and then we'll wait for the next wake up to choose another CPU, which is not always, I mean, the stability of the system is not always sustainable, and the change can happen quite often. We have other things that, yes, we have a quite aggressive, so the overutilized mode. It's a way that, so we are using the energy-aware scheduler, but we consider that when the system is overutilized, that doesn't mean that it becomes meaningless to try to do some power optimization for several things, because everything is running at max. So wherever you are running at max. And also because at some point, the task utilization that we are tracking is reflecting more how much CPU you can get while you're sharing the CPU with other tasks, more than what you would like to use. So the estimate of the energy consumed by the task become less accurate. And yeah, and based on that, based on this aggressive, so the overutilized, so yeah, we are quite aggressive to disable ES right now, for mainly because we have this only at wake up, and if we have some what we call misfit task, for example, that's a task that doesn't fit anymore on the current CPU, because we need to wait for the next wake up right now with ES. The only way that we have to migrate the task will be to switch back to the normal behavior where we are looking for enough spare capacity to migrate the task. And once we have migrated this task, we can come back to the ES. The main problem is that by doing that, it's not only this task that can migrate, but all the other tasks as well. Because we are no more aware, we are not doing any more aware scheduling. And the last point that is coming more and more, it's the scheduling latency. So we are only doing some CPU selection based on the energy impact. We don't care if the task want to have a deadline to execute, to process what you have to do. It's really only about energy. And we have more and more small tasks that want to run first or before the other one. And that we call the scheduling latency. And we are trying to include this scheduling latency in the CPU selection. So the change that we have proposed and that we are going to propose. So instead of waiting for the wake up to select another CPU, so we want to add new event where we will look for an efficient CPU for the task and migrate the task if needed. One is when the task is put back in the enqueue list. So the task run on the CPU for a slice, and then he has to wait for the next slice for it. And in this case, we take the opportunity that instead of waiting, maybe we should migrate on another CPU. The main advantage is that we are sure that we are not running, so we don't have to do any kind of active migration and so on. It's easier for us. And it's easy also in the sense that we will look at one task at a time. So from a scalability point of view, we don't have to look at 100 CPU or 1,000 tasks on 100 CPU. So it's really bonded. The time to process it's bonded to one task at a time. And yes, we are, so if you're alone on the CPU, you will not be preempted by another task. So you will not be put back on the enqueued list. So that the only case where, in this case, we can directly look at the running task, because that we don't have anything else to look at. So for that, we are using what we call the push mechanism, which is not used in FAIR. So the RT and the deadline scheduler are using the push mechanism. In the FAIR scheduler, by default, we are only pulling tasks. So a CPU will look at the load of the CPU and will pull some tasks if needed. That's the default behavior that we have. Except there is one exception for active migration, but I mean that's really when we want to migrate the active task. But yeah, so we want to enable the push mechanism as a way that one CPU, instead of looking at others to pull a task, it will look at another CPU to push the task. This keeps the scalability because we are only taking care of what I mentioned, one task, instead of looking at all the other CPU, all the tasks on all the other CPU to make sure that we can find something. And also, we want to add some new hints. What we call the less loaded CPU and the latency hint. And the less, so I will go there. Yeah. The less loaded CPU is just that it's a bit different to what we are doing right now. Right now, we are looking at the CPU with the highest spare capacity, because by default, if you have the highest spare capacity, you will probably look for the lowest OPP, which seems to be fair. The main problem is that the spare capacity, the load of a CPU or the utilization of a CPU also include the block load, so the task that just finished to run. So we still consider that we will decay slowly the fact that the task was running. So a CPU seems to be loaded or utilized, but in fact, most of the tasks are sleeping. They just go back to sleep few microseconds before. So the spare capacity can, of course, be one of the best, but that's not always the case. You can have some other CPU with far less runnable tasks on that. So that's another level that we want to add. So how does it work for the ES right now? The algorithm, I would say, is pretty simple. Is that the first thing is that does the task fit on the CPU? So can we, I mean, if we add the utilization of the task on the CPU, do we exceed the compute capacity, yes or not? If not, then we estimate what will be the cost of running this task on this CPU. And by cost, I mean which OPP we will select. And then if we have several CPU in the same performance domain, which end up with the same cost, the same OPP, then in this case, if we have one CPU with only one runnable task and another one with 10 runnable tasks, we'll select the one with one runnable task, just because it helps to improve the scheduling delay. Instead of being the 11th one to run, which can be 40 milliseconds, you will be the next one, which is 3 milliseconds right now, or 4 milliseconds, that depends. But that will not, normally, that will not change the cost of the on the system. And then, so that's, all this is inside the same performance domain, and then for each performance domain, when we have several performance domains, so typically we have one performance domain for the little, one for the medium, one for the big, because they are sharing the same voltage rail, so they are running at the same frequency. And then between all these performance domains, we are looking at the one with the smallest energy impact. So as I mentioned, yes, the goal, when should we find an energy efficient CPU? So we have at wake up right now. And now we are looking at an efficient CPU when the task doesn't fit the CPU. So the goal is that instead of moving back to the normal behavior and disable ES, we will migrate the task instead of disabling ES. And also when a task is stuck on a CPU. And by stuck, I mean a task that doesn't wake up anymore, or that wake up at a very low pace, yes. So 100 milliseconds, or even 30 milliseconds is quite long at the scheduling, from a scheduling point of view. And all this can happen because you have a uclamp max, so you're capping the max frequency of the CPU, whatever its utilization. So a task that might run 5 milliseconds every 10 milliseconds, if you cap the CPU at half the compute capacity, then you will run 10 milliseconds every 10 milliseconds. So you don't have any wake up anymore, or even worse. Or because, yes, there are some thermal pressure, system pressure, or because you have to share the CPU. So if you are the 10th task to run, 3 milliseconds each task, that gives you 30 milliseconds of delay. So the current proposal is quite simple to detect a stuck task. It's mainly if its utilization or the estimate of its utilization, so that's the highest utilization value that it can reach, or even the runnable average. So the runnable average includes your utilization and your time waiting to run on the CPU. As soon as this is going above the CPU capacity, or the clamping, then we consider that we might not wake up anymore, and we will try to find if there is another CPU that's worth migrating to. And yes, that's the current proposal, and then we can see for extending that, but we want to start simple. So on the mailing list right now, it's mainly what I have just discussed, and then we would like to extend even more the case where we can migrate a task. Typically, so since 2 kernel revision now, you can set your slice duration in the scheduler in the EEVDF. So you can say, I'd like to run 1 millisecond up to 100 milliseconds. The default is 3 milliseconds. And after this slice, you will be prompted by another task, and so on. So if at some point you say, I want to run only 1 millisecond, so I'm a short task, by default, we'll try to run you first compared to one with 100 millisecond slice. But if you go above your 1 millisecond, you will be prompted to let the other task run because you have exhausted your slice. So you can run first, but that doesn't mean you will run more than others. We keep the fairness. So if at that point you are prompted because you mispredict your duration, that can happen. Instead of just waiting for whatever the number of milliseconds will be, we will find if there is another CPU where you will have to wait less time before being scheduled, rescheduled or rerun on the CPU directly to improve the delay. And so, yeah, that's the preempted of short slice. The other one is that when the profile of the task is changing, because people don't want to have fully periodic task. If we detect that your profile is no more correct, then the estimate that we did with your utilization is probably no more correct as well. So in this case, we can look for another CPU that might better fit your new utilization. And then, yeah, the last one is just because, yeah, if you're running for a long time, probably all the input that we use to make the decision are just wrong. Yeah. I mean, they are not relevant anymore, so it's worth looking if there is better CPU to run on. That's what we are going to add on top of what we have right now. So for the long, yes, I mentioned the 32 milliseconds. It's the half-life of our load tracking mechanism. So that's why that looks like a reasonable value. Yeah, so in the list loaded selection as well, so yeah, in addition to the list loaded, we want to add few more in for the decision. So for example, if there are 2 CPU and one with a longer slice and the running task has a longer slice duration, if you are scheduled on this CPU, you will run first. Whereas if there is another task with a shorter slice, you will have to wait it before being scheduled. So in this case, why not selecting the one where you will run directly? That will improve your scheduling delay. Yeah, that's almost the same, this with the latency constraint. It's all about, yes, trying to improve the scheduling delay, the scheduling latency of short running tasks. And the other things is that BS, yes, BS, the energy decision. So right now, the final decision between 2 performance domains, between big, medium, and little, is really the energy difference, so how much energy you will consume. Now, if the energy difference is 10 microwatt in the estimation of the computation, so we are not even sure that that's the reality, we should probably not only look at the energy, but see if there is any performance improvement for the cost of 10 microwatt, for example. 10 microwatt across when you are consuming 10 watt. I mean, that's smaller than our precision in the computation. So in this case, we might use a bigger CPU, for example, but you will run faster. So for that we would like to do that. The main difficulties is that to decide when we consider that the difference is small enough that it's no more meaningful. And for that, we don't want to add a knob. In the scheduler, we don't like to add any knob. So I'm pretty sure that for some people that will be 10 microwatt, for the 100 microwatt, or even 1 watt, I don't know. So we need to find a way to bias this value without adding a per platform configuration. I'm moving to the second part. Do you have any question for the first part? No? The second part is for years now, we are discussing about how to provide some latency into the FAIR scheduler. So there was a lot of discussion using a nice latency value, which was an idea, a QoS interface. And this proposal is about using the sched set attribute. So right now for the deadline task, the hard real-time deadline task, you set a runtime, a period, and a deadline. And the goal is to reuse this field for a FAIR class. And how we can use this or take advantage of this to make a better scheduler decision. Or how we can use that to describe different type of tasks. So that's what we have tried to do. Using these 3 fields, how we can describe some. So for now, we have identified 5 different types of tasks. The fully periodic task. So the sporadic latency sensitive, yeah, there is a number. I will come back on this later. But yeah, we have identified 5 different types of tasks and how to describe them with these 3 fields. Yeah, and if we are able to describe that, thanks to the period, the deadline, and the runtime, we can compute some CPU bandwidth. So what will be your peak CPU utilization? So the runtime divided by the deadline. That's interesting in the sense that even if you are running 1 millisecond every 100 milliseconds, but you need to finish in the next 2 milliseconds. So your average bandwidth, CPU bandwidth, 1/100, it's 1% of the CPU. But in fact, you need 50% of the CPU bandwidth to match your deadline. So that's a way to easily describe, I'm a short running task, but I want to run fast because my deadline is in 2 milliseconds. So yeah, we can have the average bandwidth as well. So we can make sure that in average on the CPU, we will not be overloaded. We can have some delay, but will not be overloaded. And then for the tasks which only set their utilization, their runtime, we can estimate what we call the util average value. So the CPU capacity for a long time. So the utilization of the CPU that we are using, it's a load tracking mechanism. It's moving average way to compute the utilization. So by that, we can estimate what will be your utilization if you are running 10 milliseconds, 100 milliseconds, and so on. Instead of trying to estimate, in this case, we can just set, okay, the final value will be this. Even if we are tracking, we know where we are going, instead of waiting for reaching the max value. So that's what I mentioned. The goal of using this is to override the utils kernel scheduler value, which is an estimate of your utilization. And in addition, the goal, we could use this value not only for the scheduler, but for the interconnect bandwidth, because you might need to increase the DDR bandwidth, the interconnect bandwidth, and whatsoever, or even your L3 cache bandwidth. So I don't know, I think, so the latency sensitive task, yes, that's probably the one which is the most interesting for us. That's the one where you only have a runtime and a deadline, but you don't know the period, which most of the system, interactive system, you will have an external event that will trigger a number of tasks and process to do. But you don't know when this will happen. You just know that when it's happened, you will have, I don't know, 6 milliseconds, 8 milliseconds, if you are linked to the display of a frame to execute. And this can be easily described there with the runtime and the deadline, from which we can get this peak bandwidth to make sure that the compute capacity will directly move to the highest enough OPP to finish your job by the end of your deadline. With the sum, we can also estimate if we can ensure the deadline of all the tasks which are runnable on the CPU as well, by the sum of this value. The fully periodic task, so yeah, when you have all the metrics, it's quite easy. You can have a lot of information. Unfortunately, that's not the one. We don't have that much user space that can describe such a fully periodic task. We have few of them, and I would say that if we are really sure, maybe the task should migrate to the deadline scheduler. If you are sure about your deadline, your runtime, and your period, directly move to the deadline scheduler. The sporadic runtime one, so the one where you only know the average runtime, but you don't know when you will start, you don't have any real deadline, and you don't know the period. Nevertheless, we can still have a better utilization, because with the load tracking that we have right now, the load tracking includes the sleep time between two runtime. So your utilization can vary from one runtime to another one, just because you have sleep 100 milliseconds or 1 millisecond. In this case, you just filter the sleep duration. And then we start to have some random latency sensitive stuff. So we don't have much for that, but at least we are sure about the maximum duration of the task, even if we don't know if that will be 1 millisecond in the next 10, but at least we know that will be less than 10, and we can still set the slice duration and set some minimum utilization. So what next? Right now, the goal is to run more tests on Android. We are using the Pixel 6 for that, which run with the Android mainline kernel, which is close to 615 RC5, which is a good way to test latest change. We also want to test this scaled set attribute with ADPF, which is part of the Android framework to set some constraints. And also, yeah, the goal, the next step will be to look at the group of tasks. Right now, we are setting per task, but some people, some user space, complain that we can set the default, we can characterize a group of tasks, but not one task. And in this case, we are going to look at directed acyclic graph and things like that. But that will be for the even for the timeline. And that's it. And we are running out of time, so if you have any question, we can discuss that in the hallway. Thank you.